All right, in here I'm going to do the answer key to the packet, and I'm going to start with the kinematics, rotational kinematics. So here it says how fast in RPM, meaning revolutions per minute, must a centrifuge rotate if a particle 7 centimeters from the axis of rotation is to experience an acceleration of was that 100,000 Gs. Okay. I think the first thing I want to do is talk about the RPM, because everything has to be in radians per second. So how do I go from radian per second to RPM and vice versa, right? Or even RPS sometimes, revolutions per second. So let's just take a number, okay, in RPM. And I want to change that to radians per second. So the question is, how do we do that? Well, so this is revolutions per minute. So I'm going to do my dimensional analysis per 1 minute. Okay, so I want to get rid of the revolutions, and then I want to replace them with radians, and then I want to get rid of minutes and replace them with seconds. When each revolution has 2 pi radians, going around the circle is 2 pi. Each minute has 60 seconds. So if I have RPM and I want to switch to a radian per second, all I have to do is multiply by 2 pi and divide by 60. So let me just write that here somewhere. So from RPM to radians per second, what did we say? You multiply by 2 pi and divide by 60. You didn't even have to do the dimensional analysis to see it. Each revolution is 2 pi, so you multiply the number of revolutions by 2 pi to get the radians. And each minute, which happens to be at the bottom, is 60 seconds. So you make, instead of 1 minute, you make it 60 seconds, and you're pretty much done. Now, to go from radians per second to RPM, you just reverse the process. So you multiply by 60 and divide by 2 pi. Now, how do you go from RPS, revolutions per second, to radians per second? Well, the second is the same, so each revolution is basically 2 pi. So you multiply by 2 pi basically. Okay, so we're going to keep that in there, and we're going to do some of these problems. How fast in RPM must a centrifuge rotate if a particle 7 centimeters? So first of all, we have to change that to 0.07 meters from the axis of rotation is to experience an acceleration of a 100,000 Gs. So I think we have to say that A, C is R omega square, right? So this is 100,000 Gs equals R, which is 0.07 times omega squared. So if you do omega, you should get oh, this is no, this is more. Okay, this is a million Gs, a million meters per second squared. It's 100,000 times 10. So the omega will be 3779.64 radians per second. Now to change that to RPM, you just multiply by 60 and divide it by 2 pi. Okay, and you should get 36,092.95 RPMs. That's pretty fast. Okay, but you have to bring it up to a million Gs. That's a lot of acceleration. Okay, the next question. A 70 centimeter diameter wheel accelerates uniformly from 160 RPM to 280 RPM. So maybe we should change this RPMs to radians per second. So we multiply those numbers by 2 pi and we divide by 60, and I have the answers here, so I don't want to do it. So the 160 is 16.76 radians per second, and the other one is 29.32 radians per second. Okay? Yep. Okay. So the first question is saying determine its angular acceleration. So we're looking for alpha, which is change in omega over time, or you can say, well, omega final equals omega initial plus alpha times t. Same equation basically. Alpha equals, the change is 29.32 minus 16.76 divided by 4 seconds, and we should get an alpha equal to 3.14 radians per second squared. Okay. Okay, the next one is to find the radial and tangential components of the linear acceleration. So I'm going to start with the radial, which is basically centripetal. So we're looking at part B here. Okay, I think that's just R. R omega square. Okay. But we have to find the omega at 2 seconds, which is, yeah, we have to find that. So, because this is talking at exactly 2 seconds. So the omega at 2 seconds is equal to the initial omega plus alpha times t, and omega initially is 16.76 plus 3.14 times 2 seconds. So that omega at 2 seconds, basically this is at 2 seconds, equals 23.04 radians per second. This is not a multiplication, this is just saying at 2 seconds. Okay, so the centripetal acceleration is R omega square, which is basically that's the diameter, so it's half of that, so I guess it's 0.35. Yeah, 0.35 times 23.04, you gotta square that. This formula we derived in the previous video. So if you do the math there, we should get 185.79 meters per second square. Now we're going to try to find the linear acceleration, okay? So A tangential is equal to R times alpha. So this is going to be 0.35 times 3.14, and that should give you 1.1. That's 1.1 meters per second square. That's linear stuff, okay? Okay, so that's done. All right, let's look at number 3. Okay. Find the centripetal acceleration. So we're looking for AC. Okay. On a kid sitting on the outside of a merry-go-round that has a radius of 7 meters, the angular speed is 0.7 radians per second. So this is pretty straightforward. It's R omega square. The R is 7. The omega is 0.7. You got to square that, and you should get 3.43 meters per second square. All right, let's look at number 4. Okay. A record player rotating at 45 RPM. So maybe we need to figure out what 45 RPM is. Maybe we're going to need that. Okay, so what did we say? We multiply by 2 pi divided by 60. So let me see if I found that. So it's 4.71. I'm just going to put it there just in case we need it. Okay. Question A. What is the final angular speed of the record player? Well, here it says that it comes to stop, so I guess final omega is 0 radians per second. Part B. What is the angular acceleration of the record player? Okay. So So if I want to find the angular acceleration, I know the time, I know the initial omega, which is 4.71. I know the final. I think I can do this. Delta omega over time equals 0 is the final, minus, starting with 4.71 over, takes 10 seconds to do this. So this alpha is negative 0.471 radians per second square. Part C, what angular distance, so we're looking for the angle now, right? What angular distance did the record player travel in coming to a stop? So I think we can do this equation. Delta theta equals the initial omega plus the final omega over 2 times t. So this is 0. This is 4.71 over 2 times 10. And that should give us 23.56 radians. Right, so if you want to change that to how many rotations or revolutions, you divide it by 2 pi. Okay, I think that should be clear. Now, could we have used another formula here? Yeah, we could probably. We have choices here. Delta theta equals omega initial times t plus 1/2 alpha times t squared. You can do that. But I think the one I did earlier is simpler. All right, number 5, it says a record player that plays records with a diameter of 15 centimeters. So the radius is 7.5. So it's 0.075 meters. It's switched on, so which means it started from rest. Okay, and reaches its plane speed in 2 seconds. So the time is 2 seconds. The angular acceleration, which is the alpha, is 2 radians per second squared. What's the plane speed? So we have to figure out the omega final. So I think we can do omega final is omega initial plus alpha times t. This is 0. Alpha is 2. The time is 2. So this is going to be 4 radians per second. Okay. What angular distance did the record player travel during this period? So we're looking for an angle here. So we're looking for the angle. So how do we do that? We can probably do it without the, I think we have multiple ways of doing it. So I'm just going to do it without the acceleration formula. Okay, so this is gone. The final omega is 4 divided by 2. That's 2 times 2. That's also 4 radians. How many rotations did it make during the 2-second period? So to go from, so you have 4 radians, and each rotation has 2 pi radians. So I think the number of rotations is just going to be 4 over 2 pi, which is 0.64. So about 2/3 of a rotation. Okay. D. What is the tangential speed of a speck of dust on the outside edge? Okay, so I guess V equals R omega. This is all in your formula sheet or in your packet. 0.075 times an omega of 4. And your answer should be 0.3 meters per second, not radian per second. Okay. A basketball player spins a basketball on his finger. The ball must spin with a minimum speed of 1 RPS, so that's rotations per second, to remain on his finger. If he starts the ball spinning at 10 RPS and it decelerates at 0.5, how long will it remain on his finger? Okay, so I think we have to say omega initial. It's 1 rotation per second, so that's 2 pi radians per second. Each rotation is 2 pi. The final omega is 20 pi. It's 10 times 2 pi. Okay, the alpha, since we are decelerating, is negative 0.5 radians per second squared. We're looking for how long it will take. Okay, how long will it stay on his finger? So I think we have to use this one here, the most linear one. So we're going to put in 20 pi here, 2 pi here, negative 0.5 there, and the time should be 113.10 seconds. The next question is, how many rotations will it have traveled? I think we can find the angle and change it to rotations, right? So that's going to be, the reason I can't, I think we can just do everything in terms of rotation. So let's try it both ways and see what happens. Over 2 times t. Okay. Yeah, I think we can just do 1 here, 10 for the other one, divided by 2 times t. Times t, which is, we found it earlier, 113.10. So what is that? 5.5 times 113.10, that's going to be 622 rotations. Okay. Number 7, as you are leaving a building, the door opens outward if the hinges on the door are on your right. So basically, this is the door, the hinges are here, okay? And it's going to open out like that, okay? So if it opens out like that, we're trying to find the angular velocity. So you put your 4 fingers in the direction of rotation, your thumb will be in the direction of the velocity. So this has to be down. Number 8, at a certain instant, a compact disc rotating at 210 rotations per minute is rotating at that. What is its angular speed in radians per second? I guess this is easy, right? So it's 210. Each rotation is 2 pi, and each minute is 60 seconds. So if you do the math here, you should get about 22 radians per second. Okay, a machinist turns on the power to a grinding wheel at t equals 0. The wheel accelerates uniformly from rest to 10 seconds and reaches an operating angular speed. So this is the omega final. That's the time. The wheel is run at an angular velocity for 30 seconds. And then power is shut off. Okay, so we're trying to find how many revolutions. So I think we should find how many radians and change it later by dividing it by 2 pi. Okay, so in the first phase, we're going to do delta theta equals omega initial t plus, we don't have the acceleration, so maybe we should just do omega initial plus omega final over 2 times time. Okay, time is 10 seconds, this is 0. I think we can find delta theta to be equal to 290 radians. Okay, for the second part, we go in at a constant angular velocity for 30 seconds. So I think we can just say, well, the average omega is delta theta, I guess I call this delta theta 1, theta 2 over time. So delta theta 2 is going to be equal just 58, right? Because that's the speed you were going at, times 30. So that should give us 1740 radians. And for the last part, now we're going to slow down, right? Yeah. So we're going to do the one that doesn't have time in it. I guess I'll call this theta 3. So we're going to come to a stop. This omega here is the 58. 2, we're slowing down at 1.4 radian per second. And I guess we can find this delta theta 3, which is 1201.4. Now, all you have to do is add up all your radians and divide them by 2 pi to get the number of rotations. Okay. A bicycle slows down uniformly from V, 0 equals 8.4 to rest over a distance of 115 meters. Each wheel and tire has an overall diameter, so the radius is 34 centimeters or 0.34 meters. Determine the angular velocity of the wheel at the initial instant. So I guess we can say VO equals R omega O. So omega initial equals 8.4 divided by 0.34, and that should give us 24.71 radians per second. All right. For part B, if you think about that, we're trying to find the total number of revolutions, but we covered a bunch of circumferences as we're traveling. So we covered this much distance, right? This much circumferences, and each circumference is basically 2 pi. So if you want to find the number of rotations or revolutions, you do that division, and it should be 53.83 rotations. Oh, 2 pi times r here. Yeah. So you take in all your whole distance and divide it by one circumference to figure out how many rotations you've done. C, the angular acceleration of the wheel. Okay. So I think we can do omega final equals omega initial plus alpha times t, because I think we know the time. We don't know the time. No, we don't know the time. So I think we have to do it with the one without the time. Okay, I think this is 0. This is 24.71 squared plus 2 times alpha. Now to find the theta, you just take 53.83 and multiply by 2 pi, because each rotation is 2 pi. And you would get an alpha equal to negative 0.90 radians per second squared. Now let's look up part D. The time it took to come to a stop. Okay. So I think we just have to do omega final equals omega initial plus alpha times t. This is 0. This is 24.71. We already found the alpha, 0.9, and the time is what we're looking for. So we should get a time of 27.38 seconds. There are other ways you can do this. So if you come up with a better, different way, that's fine.
All right, we're going to look at the RT1 on page 6. The weight is tied to a rope that is wrapped around a pulley. The pulley is initially rotating counterclockwise and is pulling the weight up. Okay, and the picture shows you that. The tension in the rope creates a torque on the pulley that opposes this rotation. We'll talk about torque another time. The weight slows down, stops, and then goes back the other way, right? Graph the angular velocity versus time for the period from the initial instant shown until the weight comes back down to the same height. Take the initial angular velocity as positive, okay? So basically, counterclockwise is positive, so which means we have to start up here, okay? And so what's going to happen is going to go up, but it's slowing down, okay? Slowing down in the positive direction based on this convention here. So it's going to stop here, so there is no angular velocity, and it's going to turn and it's going to go around in the clockwise direction, which is basically negative, and it's going to start to speed up. So So it should look something like that. Now, how do we find the angular acceleration graph? Well, all we have to do is the slope of the velocity at the slope of the line in an angular speed time graph. So it should be negative because that slope is negative and it should be constant. For RT2, a block is placed on a rotating disk and moves in a circular path. The disks have the same rotation rate, which means they have the same omega basically in each case. But the masses of the blocks and their distances from the center vary. Okay. Rank the magnitude of the frictional force. So now what's keeping this from sliding out is the force of friction. So FF is basically that mv squared over r, which is basically mr omega squared. So if I want to rank the forces, all I have to do is rank the mr omega squared. They're telling me they have the same rate of rotation, so the omega is the same. So all I have to do to rank the force of friction is to rank the product of m and r. So m and r is 12 in here. And I actually don't have to change r to meters because I'm just comparing. So this is also going to be 12, this is going to be a 5, and this is going to be a 10. So it should be A and B tied for first place. D comes next, and C comes last. Right, and that should be it for this video, and I think the next video will talk about this concept of torque. All right, take it easy.